Good morning. It's a pleasure to be here, and thank you, Björn and Lars, for inviting me. And it's always fun to present to you some nice pictures and try to understand what's behind the nice pictures. So basically what I would like to do is to describe today how, by using cryo-TEM, we can actually look into the structure of the complexes that are formed by polyelectrolytes and by inversely charged, oppositely charged amphiphyles and lipids. And the emphasis is on the connection between the nature of the molecules to the complexes that are formed and to their function on the macroscopic scale. So let's start with a few color pictures. This is the Haifa Bay, seen from Mount Carmel. And as John showed us yesterday, some Dutch tulips, I felt I have to show you some Israeli wild orchids. And this is one of them. This was taken just a few weeks ago on Mount Carmel, not far from our campus. Okay, I'm afraid that the rest of it will be in black and white. So to start with, let me just thank the good people who gave us the money to do what we like to do. And of course, my collaborators at the Technion, the Technical University of Berlin, University of Wisconsin, and the Hebrew University of Jerusalem. So the basic technique that we use is cryogenic temperature electron microscopy. And basically what we do is we take a small drop, about 4 microliters of our suspension or solution, put it on a copper grid which has this kind of film on it. And then we blot it to form a very thin film and we plunge it in liquid ethane at its melting temperature. And by doing this, we're able to vitrify our specimen, which means that we make it into a glass-like material and not into a crystal, because crystallization will change the structure of what you see in your specimen. So basically, we get very thin films, each one supported on one of these holes in the holy carbon film, or the perforated carbon film. This is a cross-section through one of those holes. And you can see the dimensions of the thickness of the dimensions of the specimen that we use. Then, without bothering you with all the technical details, we transfer into this special holder and we get it into the microscope. And in the microscope, we keep it at very low temperature. And by doing this, we are able to look at the vitrified specimen for a very long time. Now, this is an old type of microscope, and actually much of the work that I'm going to describe today is done on the old type microscope. Nowadays, we have moved on, and we have a microscope that looks like this. My students say that it looks like an ATM, but actually you put money in all the time rather than withdraw. This is what's inside the box. Actually, this was as installed about a year and a half ago. And later on, I will describe some of the very nice features of what we have in that microscope. So let's start and go back in history a little bit. This goes back about 15 years ago. And this work that was done on oligonucleotides complexed with a quaternary ammonium surfactant, or quaternary ammonium lipid-like structure. And the idea was to form a complex that can be used for transfection. That means can be used to introduce genetic material into the nucleus of the cell, part of genetic medicine. So this is one example. Of course, we used also DNA. The picture that I'm going to show you is this, with this workhorse of transfection, which is called DOTAP. So there's a very strong interaction between the positive charge here on the negative charge of the DNA or the oligonucleotides. And what you see in TM, and this is our first micrograph, what you see here is this lamellar structure. And this lamellar structure is very similar, and it agrees well with scattering experiments of Saffinia and others. So this is something that was to be expected. As you will see, this kind of structure is the very typical structure when these two kinds of species get together. And as I will show you in a couple of slides, this is actually essential for good transfection. So if it's not in the lamellar phase, you don't get any good transfection. Let me just make a couple more comments. I put it here red, low-dose cryo-TEM. And by this I mean that all the images that you will see were taken with as few electrons as possible. This is essential because the electron beam is a very strong ionizing form of radiation. And if we are not careful, the structure will be destroyed before you are able to record the image. So we take our images with about 100,000 times less electrons than what typically biologists do when they look at dry specimen. Of course, this leads to some noisy images, but it's better to record noisy images of the real structure and not something that has been changed by the electron beam. The other thing that I would like to mention is that this is taken at low temperature. It's kept, as I said before, in the microscope at low temperature. And we use no stain whatsoever, no stain that may actually alter the specimen. Okay, another example. This is a few years later. We worked with Nick Abbott at the University of Wisconsin. And we looked at this very interesting lipid-like structure, which can be in two forms, the reduced form and the oxidized form. The reduced form actually gives you a very good lamellar structure. And as it turns out, in the Petri dish, it will give you very good transfection. On the other end, if you go to the oxidized form, the lamellar structure has disappeared. And when you try to transfect with this, you get no transfection whatsoever. So again, it is very obvious that you really need to have the lamellar structure. Now, the other thing that is very well known in the transfection community is that you get excellent transfection in the Petri dish, and then you get lousy transfection in the animal model. And the reason for this, apparently, is that when you add blood serum to your Petri dish, or to your specimen in this case, you see very well that the nice lamellar structure that we had, those nice complexes that we had, have now disintegrated. All the spaghetti that you see here is actually the free, in this case, DNA that is completely free now. And of course, in the free form, it cannot give you any transfection. By the way, I looked again at those pictures yesterday, and we see on the DNA, we see quite a bit of dark dots, very dark dots. Before that, I tended to interpret those as ends of the chain looking up towards us. Following yesterday's talk about the knots, we may actually be able to resolve the dots, the knots, all these black dots. This is something that I'll have to go back and look more carefully to, but I don't see Patrick here, but anyway, I should thank him for that. All right. Now, following that, and much more recently, we tried to understand how does the nature of the surfactant or the lipid and the nature of the polyelectrolyte affect what we see in our micrographs. So we would like to see the structure. So for doing this, we selected two polyelectrolytes, which are quite different, synthetic polyelectrolytes, excuse me. One of them is sodium polyacrylic acid. The other one is sodium polystyrene sulfonate. This one is quite flexible. This one, it's quite stiff. This is fully dissociated at all pH values. And this one has a pKa of 4.2. So these four allow us to get some insight of how aggregation, complexation, is governed by the nature of the materials. So, and the lipids, we took again the same workhorse that we saw before, the DOTAP, and a very simple one, didodecyl dimethylammonium bromide, which is really a very flexible, very easy to work with material, and we now will see how the structure develops with these two. So if you take DOTAP, and the same thing goes for the DDAB, you get just simply vesicles. By the way, have a look at the length of the bars. And at a charge ratio of 1 between the two, we get the same kind of lamellar structure that we got before. Actually, this part is going to be quite uninteresting because everything you do, almost everything you do, gives you the same kind of structure. But this is actually quite interesting because whatever you change, in this case it's DOTAP and PAA, you see we get the same kind of lamellar structure. DOTAP and PSS, doesn't matter what is the molecular weight of the polyelectrolyte, still you get the very same kind of structure. DOTAP and PAA, you change the charge ratio, still the same kind of structure. Again. And now let's look at the effect of pH of the solution. So we'll start with high values, and again, we get the same kind of structure. By now, you are used to it. Still above the pKa of the polyacrylic acid. And when we go down below the pKa of the polyacrylic acid, you can see very well that the lamellar structure has actually disappeared. More specifically, there's really no interaction between the two species. One thing that you could have asked is, what about the sizes? Okay, the spacing between those in this lamellar structure. So it's very difficult to get those sizes from electron microscopy. I love electron microscopy, but I must admit that it's not the best quantitative tool. It's an excellent tool to identify what are your structures, to identify the building block of your structure. If you have those, you can build a physical model of what you have in your solution and then analyze it by other techniques, more quantitative techniques like small angle X-ray scattering, and get the structure and get the sizes from this structure. And this is exactly what we did. I'm not going to bother you with the details of the small angle X-ray scattering, but just show you that actually there is a big size difference if you compare these two things, the DAB with the polyacrylic acid and the DAB with the PSS. And this is related, without getting into too many details right now, to the interaction between the polyelectrolyte, the water, and the surfactant. And there's quite a bit to learn from this one. Okay, saying this, let's move to the present. This is not that old. This was published about 1.5 years ago. So let's go now to the present. In the present, we have a new microscope. And it's not that only we have a new microscope. The community has new microscopes which can do much better things than what we were able to do before. The first thing is that we have much more sensitive electron cameras. And what you see here, this already comes from the new microscope. What you see here is the same specimen. This has nothing to do with the topic of our conference, These are carbon nanotubes, dry carbon nanotubes, the same area taken with two cameras. The old style camera, which involves scintillation, and the direct imaging camera, which is called the Falcon. This was done on the Falcon 2. Now we have upgraded it to Falcon 3. This was taken, those two pictures were taken at the very same conditions with very, very low electron exposure, just 2 electrons per angstrom squared. And what you see very well is the big difference between the two. Now, it's not just that you can take better looking pictures. That's important too, of course, especially when you give a lecture. But what is important is that you are able to collect your information with much less damage to your specimen. And you can see here that the dynamic range is much better. And here it's a little bit noisy because of the low electron dose. And here it is really quite nice. The other feature is called faceplates. And this is completely analogous to faceplates in light microscopy. Our problem in imaging is that when we shine a beam of photons or electrons in our specimen, the rays that come out, the beams that comes out is changed by amplitude and phase. We can see the difference in the amplitude. We cannot see the difference in the phase. And some objects give you very little amplitude changes and quite a bit of phase changes. So what the faceplates do, and this goes back to the times of Zernike in the 1930s, the arrangement that you see here simply allows you to convert phase changes into amplitude changes. The same thing is available now in electron microscopy, finally. It works a little different. It's using not real faceplates, but a thin film of polymers which is charged by the beam. And what it does the same thing as the Zernike faceplates. So what you see here, or rather don't see here, is a collection of trimers of proteins suspended in the liquid. And this is taken in focus in the TEM without the faceplate. Now, pay attention to this thing here. This is actually a speck of ice. And now I'm going to turn on the faceplates. Okay? I think it's a little better. Okay? And this is really a very important thing because many of the objects that we are interested in soft matter, really have very, very little contrast. And this is actually going to make a big, big difference in our work to come. This is just, this slide was given here to show you that we can do the same, that we can do cryo-TEM, not necessarily in aqueous systems. These are carbon nanotubes suspended in chlorosulfonic acid. And using faceplates, you can actually resolve the two walls of a carbon nanotube, which is just 2 nanometers apart, in the liquid. Okay, so as you can see, we have now much, much better tools. Very briefly, this is a type of microemulsion that comes from the laboratory of Michael Gradzielski at the Technical University of Berlin, and it's based on polyelectrolytes and surfactants. And I brought it here briefly just to show you that without the faceplates, we can see very little. With the faceplates, we can see very well the thread-like structures that are found at a certain composition of this microemulsion. Okay, knowing that we have a very strict chairman, I'll move right away to the, I'm just as bad, don't worry, don't feel bad. I'll move to the very last topic. And the last topic that I'm going to show you, which takes me about 4 minutes, will, Mr. Chairman, will illustrate or will try to explain why we lose transfectionability when we add the blood components. So what we thought would be the problem is that some of the ingredients, some of the components, rather, of the blood actually interact much stronger with the polyelectrolytes, and by doing this, destroy with the lipid, and destroy the complexes. And this is really the case. So what we did first, we took the same lipid, artificial lipid, DOTAP, and we interacted it with bovine serum albumin. And sure enough, we got structures that were very, very similar to what you get in your complex. So this is without the polyelectrolyte. And you see very well, actually, that between the bilayers, there is another fainter layer, and this is the protein that is simply trapped between the two. If that is the case, we are in trouble. Actually, we tried it also with the more simpler surfactant, with the DAB, and you can see very well, again, the same kind of structure, bilayers with the protein attached between them. So this means that BSA, and as a model for other components of the blood, could easily interact with our lipid, and by doing this, take the complex apart. So we gave it a try, and sure enough, when you take DDAB plus PAA and incubate it overnight, and you know already from the first part of the talk that it gives a very nice structure, lamellar structure, and then you combine it with BSA for just a few minutes, you see that your entire structure is now destroyed. And the same thing goes when you have the DDAB plus BSA and you add polyacrylic acid, again, because of the interactions, you get some kind of destruction, not so much because PAA is not as strongly binding as the BSA, but apparently, and this is work that we are still doing, apparently the competing species really lead to the destruction of our complexes, and this is something that people will have to think when they engineer their complexes. Okay, so that's it for now. I hope I gave you a taste of what modern cryo-TEM can do, and the fact that really you can connect the nature of your molecules to the nature of the complexes that formed, or any aggregates in that matter, and to the function on the macroscopic scale. Thank you very much.
Thanks, Ishi, very much for this very beautiful talk and sharing with us these beautiful pictures. Questions, please. Please. The microphone here.
Yes, really impressed by the very, very beautiful images of that microscope. Though I have one question. As you know, the process of the complexation between macromolecules and even surfactant is a kind of metastable, which it has a very long reaction time, which get eventually to the most stable state. So you should be very carefully in which process, I mean, you have to carefully observe the profiles of time after your reactions. And I'm curious in which process you are focusing. And the image is changeable with the time, and that's my question.
Okay. Quite often we are interested in the evolution of a structure.
Yeah.
I must admit that in this type, in these systems that I showed today, we haven't really gone into the time history of this. We were more interested to see what actually happens after a relatively long time.
Oh, yes.
In other cases, and this is work not published yet, we have even looked after 2 weeks and 3 months, and in some cases we do get changes, and some cases we don't. So again, this is really interesting. It's a good point, and this is something that we are quite aware of, definitely. Thank you.
Oh, yeah. So at least the images are right after the mixing. Yes.
Well, most of the images that we have done, that I've shown here, were taken about 24 hours after mixture, and we did at one point, at least in these systems, looked after 1 week, and there was no difference in this case.
You don't have any.
But we have not tried to capture. We have done it in other systems. We have not tried to capture the history or the process of development. Not in these.
Okay, thank you.
Please, Gero.
Do I have to switch it on? Well, I'll do it this way. Beautiful images, of course, but you showed one where you complex the lipid with the polyacrylic acid and the polystyrene sulfonate. Now, when you look at the charge density or charge-to-charge distance in a lipid bilayer, that's about 6 angstroms or 6.5 or something like this. If you look at the charge-to-charge distance in both polymers in the fully dissociated state, you're at 2.5. So we have a mismatch of the charge-to-charge distance. The two images that you were showing showed an interstitial space between the lipid bilayer that was smaller for the PAA, for the polyacrylic acid than for the polystyrene sulfonate. Can you tell me where this is coming from?
Well, this, as I said very briefly before, you have to take into account the interaction between the surfactant, between the lipid, well, the polyelectrolyte, and the water, and the polyelectrolyte and the surfactant. Now, you have to take into account that PSS is much more hydrophobic, it is much stiffer, and it has a stronger interaction between the charges. Because of that, and PAA is much more hydrophilic and much more flexible, and this is reflected in what we showed. And the argument actually agrees quite well with what we got as sizes from small angle X-ray scatters.
I would have thought quite the opposite, because the polyacrylic acid can dissociate, so it can adjust its charge to charge distance.
Both are fully dissociated
fully,
at this point.
okay.
Both are fully dissociated at that time. And of course, you know, this is what nature gives you. So
Of course, yeah.
just argue with her.
Yeah.
Very good answer. So, maybe just one question to this fabulous new instrument. Is it what is it? Is it a trick, or what does it better than the old ones? Is there some correction in it, or?
No, it does better everything. It has better optics. It has a better interface between the operator and the instrument.
Okay.
And then it has what I showed. It has better cameras and the faceplates, of course. Also, this instrument is 200 kilovolts, while the older one was 120. Now, you want to use a corrector when your resolution is not limited by your specimen. So there's no need in most cases. There are some cases. There's no need for this kind of work to actually work in the cryo state with a CS-corrected instrument. Although one can think of an exceptional system that will benefit from that.
Well, we don't have anyhow the money to buy this thing. So let's thank Ishi again.
Thank you very much.